Today we're going to be continuing our note on limits. So yesterday we did talk about number 1 right here. So we were substituting numbers right into our limit. That won't always be possible. So today we're going to focus on the next 2 types. I'm going to start with the third type right now, so a table of values. So what you're going to see here is if I plug in 0 right into this limit, that's impossible. I'll get an error. We know that we can't divide anything by 0. So I'm not able to substitute just like I was yesterday. If I'm going to plug this into the table of values, I do want to show you a couple of things. So what I have here is I have some values that are going to represent the limit as x approaches 0 from the right. You're also going to notice that I have some values that would represent the limit as x approaches 0 from the left. So I'm going to start plugging some of these numbers in. If I plug in 0.01 for x right into my limit, so 1 divided by 0.1, I get 10. 1 divided by 0.01, I get 100, and then I would get 1,000. So what I'm noticing is that these numbers are getting bigger or closer to infinity. I'm able to say that the limit as x approaches 0 from the right of 1 over x equals positive infinity. Now I'm going to do the exact same thing for x approaches 0 from the left. So 1 divided by negative 0.1, I get negative 10, negative 100, and negative 1,000. So what I see here is that these values are approaching negative infinity. So again, I'm able to say the limit as x approaches 0 from the left of 1 over x is negative infinity. Now, just like we talked about yesterday, if the limit as x approaches from the right and as x approaches from the left is equal to the exact same thing, then we could say that that limit exists. Since these answers are not, one is positive infinity and one is negative infinity, we know that this limit does not exist. I'm going to show you what this looks like on a graph on the next slide. All right, I do have a really rough sketch of this graph 1 over x in here, so I'm just quickly going to show you in the same colors as before. As x approaches 0 from the right, I have my graph approaching positive infinity, and in green, as x approaches 0 from the left, I have my graph approaching negative infinity, and since they're not the same, this is just a visual representation of why this limit does not exist. I wanted to go through a few examples of limits to infinity. So there's one quick thing that I just want you to remember and understand. In general, the limit as x approaches infinity of 1 over x to the n is equal to 0, where n is greater than or equal to 1. So if we're dividing by x to the power of anything, as long as it's a positive number, the limit of that is going to equal 0. Now, if you think about that, or if you try it out with a calculator, you will probably see why this is happening. If I have a number, any number, divided by a super huge number, you'll see that that approaches 0. So, for example, if you have 1 divided by 1,000,000, you would get a very small number. If you did 1 divided by 1,000,000,000, that number would become even smaller. So it would get closer and closer to 0 as that huge number on the bottom increases. If we take a look at these first 2 examples here, the limit as x approaches infinity of 1 over x. If I think about the graph on my last slide, if x approached infinity, yes, my graph did equal 0. And the same thing would happen if I have the limit as x approaches infinity of 1 over x squared. It would be 1 divided by a super huge number squared, so it would also equal 0. The next two examples aren't as easy to visually see or understand. So when I look at these, I can't just substitute infinity in. I can't do infinity plus 1 divided by infinity squared. I can't simplify that. So I'm going to give you a little hint. If you see x approaching infinity with a function that looks similar to this, what we want to do is we want to divide by the highest power of x. So when I look at this first example, I have x plus 1 divided by x squared. So I'm going to take all of the terms in this function and I'm going to divide them by x squared. So dividing each of those terms, I have x over x squared plus 1 over x squared divided by x squared over x squared. I can now simplify this even further. So the limit as x approaches infinity, x over x squared is 1 over x, plus 1 over x squared can't be simplified at all, divided by x squared over x squared, which is 1. And now I can take a look at the formula that we talked about up here, or the fact that the limit as x approaches infinity of 1 over x to the power of n is going to equal 0. So I now have 1 over infinity, which is 0, plus 1 over infinity squared, which is 0 divided by 1, and 0 plus 0 divided by 1 is 0. Please note that at this line, I did drop the limit notation since I am subbing that infinity in for x. Our next example is an x approaches infinity as well. So what I'm going to suggest right now is I want you to attempt to do this one by yourself. So divide by the highest power of x, pause the video, and then when you think you have an answer, check back and I'll go through that solution for you. So here's the full solution. I've included all lines. Really, this first line that I have written in green here is not necessary, but I did include it. So I've divided every single term by x squared. In the second line that I wrote here in green, I've simplified. In the third line, I've removed that limit notation and plugged an infinity for x, and then finally got an answer of 3 over 1. We are going to continue on with these examples. So when I look at this one, I have an x approaching infinity. So I'm going to be thinking about some of the rules that we talked about in previous slides. The numerator in this function is already simplified for us. The denominator is in factored form. If you think that you could factor the numerator and have something cancel out, that is an option. But for now, I think that I'm just going to expand that denominator. After you expand out, you can go through and divide each term by our highest power, so in this case x squared. So I have the limit as x approaches infinity, and I'm going to skip a line. You can too if you want. I have 4x divided by x squared, so that's a 4 over x, minus 2 minus 3 over x squared, divided by, I've got 2x squared over x squared, so just a 2, plus 9 over x plus 4 over x squared. So again, if you want to show the line where you divide each term by x squared, you would fit that in right there. I can now substitute in infinity, so I'm going to remove the limit sign here. And I'm just going to be left with 4 over infinity, which is nothing, so 0. Subtract 2, subtract 3 over infinity, 0, over 2 plus 9 over infinity, which is 0, plus 4 over infinity squared, which is 0, and then negative 2 over 2, which is negative 1. So I really love this next example. If I think about just substituting infinity in right now, I'm going to be getting infinity squared plus 1 over infinity. That doesn't really help me. If I divide each of these terms by my highest power, I'm going to be getting a 1 over x on the bottom. And we all know that when I plug infinity in for there, I can't divide by 0. So that's not really a good idea either. What I need to be doing in this situation is I just need to be simplifying this. I can rewrite this as x squared over x plus 1 over x, and I really haven't changed anything. I've just broken this up. And now that I've rewritten it like this, sorry, I don't know why I changed colors there. I can go ahead and I can just substitute that in. Actually, maybe I'll simplify it one step further for you. X squared over x is just x plus 1 over x. And now when I substitute everything in, I'm going to be getting infinity plus 1 over infinity, which is infinity plus 0, which is infinity. So the limit as x approaches infinity of x squared plus 1 over x is infinity. So far we've gone through a few ways to solve a problem. I'm just going to back up and show you a different type of problem here. The limit as x approaches 4 of this function. So if you notice, if we plug in the 4 for x, we're going to get an answer that makes sense, and we can just solve this easy by substitution. So 4 squared plus 2 times 4 minus 3 over 4 squared plus 2, which is 21 over 18, which I could reduce to 7 over 6. The problems won't always be as easy as the last example. If I plug in a -2 here, I'm going to get a 0 in my denominator, and we know that we can't divide by 0. It's undefined. So when you see a problem like this, we do have to think about doing something else. With this particular example, I noticed that I have an x plus 2 in my denominator, but in my numerator, if I factored that, I would be able to also get x plus 2 as a factor. So now that I've factored this, I can see that I'm able to cancel out what was giving me issues. So now I can just plug in this information. So I have a -2 plus 3, which is going to be 1. So what this is an example of is a function with a hole in it. If I plug in a -2, there would be a hole there, but I can evaluate for the limit as x approaches -2, and I get that answer of 1. So another quick example where we're going to be factoring. If I plug 4 in right away, I get 0 in my denominator, and we know that that can't happen. So I'm going to rewrite this. Limit as x approaches 4. I'm going to factor my numerator. So this is a difference of squares. So if I factor that, I've got an x plus 4 and an x minus 4. I am able to cancel those out, and at this point I can just go ahead and plug in my x of 4, and I get the limit as x approaches 4 is equal to 8. All right, second last example, limit as x approaches -2. If I plug -2 into this denominator, I would get a 0, so I do know I have to do some work. I'm going to factor this numerator off to the side, just because I don't want to show all of the steps, but you could show me that work, or you don't have to. That's totally up to you. So I've went ahead and factored using decomposition in the bottom, using yellow there. And I've plugged that back in just so I don't have to rewrite limit 4 different lines. I'm going to now factor the denominator of this as well, so something that multiplies to -8 and adds to -2, so an x minus 4 and an x plus 2. And again, what I notice is that I can cancel out some of this information. Now when I rewrite this, I'm only left with a 2x plus 1 over x minus 4, and when I plug in that -2, 2 times -2 plus 1 over -2 subtract 4, which is -3 over -6, which is a positive 1/2. I am going to leave you with one last example that I would love you to try by yourself. I'm going to make another video and post it below, and it will go through a full solution for this. But like I said, I do want you to try by yourself. So I've left you with a little recall, just like a quick little jog of your memory to remember how to factor these cubic functions, and then hopefully you can factor this and solve for the limit as x approaches 1. If you do it right, you should get an answer of 3 over 2, but like I said, I will post the full solution below this video.